Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, the Director of the Composite Design and Manufacturing Hub. This webinar series examines the history, present capabilities, and the future of composites. Our goal is to share the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. Our center is located in the Indiana Manufacturing Institute. We welcome all of you to visit us and interact and collaborate with us. At the CDM Hub, our mission is to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. Our vision is for CDM Hub to become the premier resource for composite design and manufacturing. To achieve this mission, we have developed a powerful website called cdmhub.org, which serves as a platform for the composite community to collaborate and innovate together. We invite you to join cdmhub.org and take advantage of the knowledge and resources available on this website. This webinar series is made possible by the generous support of our sponsors, Dassault Systems, Cytec Solvay, and Anna Swift. We extend our heartfelt gratitude to our sponsors and acknowledge their commitments to advancing the field of composites. We also welcome other organizations to join us and also join them in supporting the global composite community. Together, we can create a brighter future for our field. This webinar will be recorded and made possible on cdmhub.org. We will email you once the recorded video is available online. And the presentation will last around 45 minutes. It's followed by Q&A section, and all attendees are muted. We ask you to submit your questions through the Q&A box to ensure the speaker has adequate time to address questions, and your questions may be summarized or rephrased. But rest assured that all questions will be forwarded to the speaker for answers at their discretion. Now, I would like to invite Professor Byron Pipes to introduce our distinguished speaker today.
Welcome all. It gives me a great deal of pleasure to introduce Tim Osswald. He is a professor of mechanical engineering and director of the Polymer Engineering Center at the University of Wisconsin-Madison. Originally from Cucamonga, Colombia, he received his BS and MS in mechanical engineering from the South Dakota School of Mines and Technology, and his PhD in mechanical engineering at the University of Illinois, Urbana-Champaign in the field of polymer processing. He spent 2.5 years at the Institute for Plastics Processing, IKV, in Aachen, Germany, as an Alexander von Humboldt professor. He received the National Science Foundation's Presidential Young Investigator Award in 2001, also the Richard Escalante's Prize Award. In 2006, he was named an honorary professor at the University of Ollinger, Nuremberg, Germany, and in 2011, he was named honorary professor at the National University of Columbia. Professor Osswald teaches polymer and polymer composites processing and designing with polymers and polymer composites and research in the same areas, in particular in the area of fiber orientation, fiber density, fiber length distributions. Professor Osswald has published over 300 papers, several books in the material science of polymers for engineering, Hanser, Polymer Processing Fundamentals, Hanser, 1998. Injection Molding Handbook, Hanser, 2001, 2007. Compression Molding, Polymer Processing Modeling and Simulation. International Plastics Handbook, Plastics Testing Characterization, Understanding Polymer Processing, Polymer Rheology. The list goes on and on. His books have been translated into Italian, German, Spanish, Japanese, Chinese, Korean, and Russian. Professor Osswald is also the series editor of Plastics Pocket Power, which currently encompasses 6 books. He is the editor of Polymer Composites, editor of the Americas of the Journal of Polymer Engineering, and the English language editor for the Journal of Plastics Technology. Professor Osswald serves on the scientific advisory board of several industries and is one of the co-founders of the Madison Group. He is part of a commission that advises the Colombian president, this is the country of Colombia, in the creation of its science ministry. And we're delighted to introduce Dr. Osswald at this time and look forward to his presentation. Thank you very much.
Thank you so much, Byron, for that kind introduction. And thank you so much for inviting me to be part of this prestigious series on composites. So my presentation today will deal with development of fiber microstructure during processing of discontinuous fiber reinforced composite materials. There are a lot more people who were involved in that I've worked with in the past few years. I've named the 4 most recent graduate students who have worked on this, and I also named there 2 of my collaborators in industry, Dr. Umesh Gandhi and Dr. Angel Yanev from Toyota and SABIC, respectively. And of course, there's a lot more people working in this field. But throughout the years, my former advisor, of course, Chuck Tucker, laid the groundwork for a lot of the work that people have worked now worldwide in this field. And you'll see probably some of his data and results throughout this presentation. So just a quick introduction for those of you who've never been in Madison, Wisconsin. It's certainly worth a visit. You can see the university in the lower right hand corner, and then there's the Capitol. We're also the capital of Wisconsin. We sit between 2 lakes, so it's a beautiful town to come to and visit, and you're always welcome. Here are some of the people who have worked on, I put arrows in their names, who have worked on the discontinuous fiber composites area. We're standing there in front of the mechanical engineering building. So they're, and of course, I'm grateful for their work and having the pleasure of being their advisor during their PhD studies. So discontinuous fiber composites, of course, is not a new thing. And this is a photograph I took years ago in Panajachel, Guatemala, where an Adobe bricks and old constructions in Guatemala are made with mud and straw, which are discontinuous fiber composites, of course, and they are what really hold things together. So it's a field that has been around for many, many years. You can see some old photographs here, the 1946 trunk lid of a Ford being hit by an axe by Henry Ford. That was made with unsaturated polyester and glass fiber. Then there was the glass fiber Corvette in 1953 that came out in June of 1953. And today, of course, the Corvette still, I should probably update that to 2024, but even today in 2024, the Corvette is still compression molded out of sheet molding compound discontinuous fiber composites. So during mold filling, of course, many, many things occur in manufacturing of these products. Fiber orientation distributions form, fiber length distributions form, fiber density distributions, and I will talk about some of those today, some in more detail and some in lesser detail. So an injection molding of discontinuous fiber composites, this would be a demonstrator part from VW. It's a VW instrument panel. Again, the mold filling is what determines the microstructure within the final part. But as we will see at the end, not just mold filling, but also the injection molding plasticating unit has a big role to play. And I will actually end up with that, which is an area of current research. So from a bird's eye view, I have these graphs. So there is the upper part is the fiber parameters alone. So fiber length has a huge impact on the properties. You can see, for example, the modulus, the strength, and the impact on the upper left side are all affected by fiber length. So fiber length is important. Fiber concentration is important. Of course, the impact strength eventually, you can see, reaches a maximum at a certain fiber concentration. Then it becomes more brittle. However, the modulus, of course, continues to increase with fiber concentration. And then fiber orientation, of course, plays a significant role in the final properties of the part. There's, of course, interactions between all of those, between the fiber density, fiber orientation, fiber length. So fiber length will, of course, at high concentrations, will start going down. The modulus eventually goes down. The fiber, and in the middle, you will have shorter fibers, longer fibers, and they will affect orientation on the right-hand side of the lower part, where the long fibers will reach lower degrees of orientation because of higher interactions between the fibers. Short fibers, of course, will be able to reach higher degrees of orientation. So this is just a little review for those of you who are not familiar with it. This is a way to represent fiber orientation distributions using the Tucker-Advani tensors. Basically, if we look at the random orientation, so a fiber is represented with a unit vector. You can see it on the left upper hand side. If we take the unit vector P1, P2, P3 with the orientation with the angles, we can generate then an orientation tensor where we integrate using the orientation distribution. We integrate around the orientation distribution. We can also measure them and just average out every fiber, and we get a general orientation tensor, AIJ, which I'll come back. I mean, I'll show some of the results and measurements that go to it. But if you see the AIJ on the top, a random orientation would be represented A11, A22, A33 as equal parameters. They add up to 1. So that's one thing that makes it easy. So 1/3, 1/3, 1/3 just simply represents a random orientation distribution. If they're all oriented, let's say in the one direction, as the lower right-hand side shows, then the orientation tensor, which is simply would have a 1 in the A11 term, and the other ones are 0. So this is just a very brief description of the orientation tensors that I will use in the next a few slides. So there's different things that cause orientation. One of them, of course, is the advancing melt front, so that you can see a fountain flow effect that leads to an orientation, a stretching in that area in the direction of flow, which lay fibers on the upper and lower surface of a molded part in the direction of flow. So it creates a skin layer in the part where you have a preferential orientation in that direction. There is, of course, also radial flow expansion that's in the central core of the part. So you usually have radial flow expansion, and so there the fibers will get oriented perpendicular to the direction of flows. So typically you will have orientation perpendicular to the flow in the central core of an injection molded part, and then you would have orientation in the direction of flow in the outer skin of that. So if we can, for example, look at an example, the part here. So this is a demonstrator part from SABIC simulated with Moldex 3D. So we have the injection molded process. We have different areas that we analyzed. You can see the middle figure on the left-hand side. Their positions 1, 2, and 3. We will refer to those. The lower part is our pyrolysis examinations that we did on the fibers to be able to predict fiber content or measure fiber content throughout the part. So if we look at, for example, location 1 in the central location in that plate, so we have fiber orientation, fiber density throughout the part. This is using polypropylene with 30% glass fibers. The original fiber length of the pellets were 15 millimeters. So this is Stamax from SABIC, and we have, if you can see, an orientation in the direction of flow. And so the upper picture on the left shows the orientation, measured orientation. The lower picture shows the normalized fiber density. And on the right-hand side is a micro CT. As we go through the thickness of the part, you can see how the orientation starts out in the direction of flow in the outer skin, and then becomes oriented perpendicular to the direction of flow in the central portion. You can see that in the A11. A11 is the direction of flow. A22 is the direction perpendicular to the flow. So these are the orientation tensors across the thickness. So we can see if we travel along the thickness of the part, you can see here how the fibers oriented in the direction perpendicular to the flow. And then I think it's a little, I think my dots are flying around a little bit more crazy. But you can see the orientation, how it changes, but also how the density of the fiber becomes higher in the center of the part. So we can do different measurements. So here positions 1, 2, and 3, locations 1, 2, and 3 in the central graph on the left, and there is obviously the measured values, and on the right-hand side with different fiber contents going from 5% fiber content to higher as we go down to higher concentrations. And so you can see the concentration of the fiber affects the orientation, the final orientation of the part in the different locations. So these are all measured values. And so many things that we did throughout working on the basis that was laid down by previous researchers, we used what we call a mechanistic model, where we model individual fibers, or also called direct fiber simulation. Here we have a simple shear flow where the fibers start out as oriented, randomly oriented in space. And so if we move the upper plate and the lower plate to the opposite direction, and we use a boundary condition between the entrance and the exit flow, you can see the fibers starting to orient in the direction of flow. Of course, there is no orientation in the second direction, so only directions 1 and 3 are changed. In the second direction, it remains still at point 30, 33, 32. You can see a final orientation in the direction of flow, and fewer orientations across the thickness of the part at 0.03. So that would be the lower tensor component. For this, we then determined what, by doing a fit in the model equation using the Tucker model, Phelps-Tucker model, where we have the interaction of the fibers as well as the length of it. So we can see in the simulation parameters using Moldex 3D, by applying the method, the mechanistic method to determine the fitting parameters, we can get fairly close representations of the fiber orientation as simulated and as measured. And there's still some discrepancies, but one of the things that the model assume is that we have a constant fiber density distribution. And as you saw, the fiber density distribution in the center increases. So we have more fibers in the center of the part or the core of the part as we do in the skin area. And so obviously we will never be able to get to a very accurate representation unless we include the variability or the fiber density distribution during processing. So we can also use this in compression molding. Compression molding is when we just simply cut charges, place them in the mold, and then squeeze them. This would, of course, also lead to fiber orientations. If we do, for example, a charge and unidirectional flow, as the work that Chuck Tucker and Larry Chen did in the 1980s, we can start out with an initial orientation. You can see the initial orientation, the experiments, which were is the data from Chuck Tucker and Larry Chen. We can see the black dots are how close we were able to get them by generating a charge with that particular orientation. So the orientation is shown in the left-hand side, but since it's very difficult to place individual fibers in a space, we had a fiber density distribution about 3%, and then simply compress them without generating any deformation. So have the fibers then interact during compression. That's the change then that you see between the original data and the simulation data, which are the red bars. So the black dots are the original data, and the red bars are the orientation in this charge that is represented on the right hand side. And so if we squeeze that in one direction, as the experiments that Chen and Tucker performed, you can see the change then in the orientation. In this case here, represented with the Advani-Tucker models. There's other things that you can see that I'll refer to a little bit later. You can see a change in the fiber density distribution, and particularly in the flow front. So if we compare the Folger-Tucker model and to the experiments by actually Jackson and Tucker, my mistake, not Chen and Tucker there, and the mechanistic model, you can see that they all match quite well, which means the mechanistic model can represent really well the orientation, and we can use the mechanistic model then to determine interaction parameters and fitting parameters for the various models that exist. So, today orientation predictions are reliable for constant fiber densities, and we know that the fiber densities, of course, vary. And the reason why this is from Tucker and Chen. The data from Tucker and Chen, where we can see the need for having orientation in the final properties. If we just concentrate on the lowest curve and the highest curve, that's in the direction perpendicular to the fibers and parallel to the fiber orientation for the 33% mold coverage. So when we have a charge that is 3 times as thick as the final part, so there's quite a bit of deformation, which is not atypical for compression molded parts. If we again look at the compression, look at it from the top, we can see a fiber matrix separation taking place. The little black box represents the actual volume of the material, and then the fibers, you can see them lagging behind. this is very typical to compression molded parts. So if you look at trunk lids and hoods of compression molded parts, the part that first starts failing in them is the crumbling at the edges. And the reason the edges crumble is because they're very, very poor in fiber content. So this fiber matrix separation is something that we need to deal with and needs to be predicted. And it's something that is not quite well understood yet. I mean, there are different models by Morris and Boulay and other models that represent fiber matrix separation and fiber migration, but they are not quite there where they should be. And software today does predict fiber matrix separation, but in many cases they don't lead to the actual distributions that is seen in parts. So the first thing that I'll show here regarding fiber matrix separation is in this, again, the three samples, 1, 2, and 3. For two different fiber contents, 20% glass fiber and 40% glass fiber. These are glass fiber. These are injection molded parts using the Stamax materials, where the original fiber length is 15 millimeters in length. And you can see there are two different techniques used to measure the fiber density distribution. The red lines are micro CT, so using micro CT and assessing the fiber density distribution using that. The second one is a more cumbersome, the little gray circles. It's a more cumbersome way of doing it, but more exact, is milling the part and just measuring the content of and burning then the powder that is milled off, and then measuring the glass content after doing a pyrolysis analysis, so it's more accurate. But you can see both techniques, the micro CT and the milling method, actually work, give the same results. So micro CT is definitely a technique that can be used to measure that fiber density distribution, and we've used that in many of our studies. So we don't have to use the cumbersome milling technique. Another aspect of fiber density distribution is taking samples, so not looking at the thickness distribution, but rather taking small samples as shown on the left lower side and doing pyrolysis on that and measuring fiber density distribution. And you can see from left to right, we go from 5% to 60% glass fiber content. There are 6 plates, and each plate, of course, has 2 halves, and it's a symmetric case. So this is so we actually have the averaging of 12 different samples, and you can see how the fiber density distribution changes with fiber content between 5 and 60%. There is a significant change in fiber density. You can see the typical filling fiber content of 20, 30, 40% that is used commercially, that there is a huge fiber density at the end of the part. And that's very typical. So if you have a part that you mold, the last place to fill usually has the highest fiber density, which is something that people are not able to predict very well yet, using models, using the Morris and Boulay model, which is the one that has been implemented in Moldex 3D at least. So you can see that effect is quite significant, and I think further work needs to be done in that. So there is certainly room for research there and for people to predict, to fine tune the models. Maybe use some of them, but for example, the effect in compression molding cannot be predicted with the Morris and Boulay model. So the last thing that I wanted to chat about is fiber length and fiber attrition. So fiber length is really important. We have these long fiber reinforced thermoplastics. We start out with pellets that are 10 millimeters long, 15 millimeters long, to be able to have at the end fiber length that is much higher, where we can use the fiber itself to its best of its abilities by maintaining its length. However, unfortunately, we can't. So this graph here actually shows the effect of fiber length. Typically, we know that a fiber length or L over D ratio of 100 is the length that we should have to retain properties, but in many cases we don't even come close to that. So the fibers get damaged significantly, and we can go to the sub-micrometer level of or few micrometers. So not sub-micrometer, but 300 or so micrometers in length, which are L over Ds of maybe 15 or 30. So fiber attrition is significant. So this is a typical. So how do we represent fiber length? So typically, what we look at is at fiber length distribution. So that's the histogram that you can see on the right-hand side of the graph. This would be a typical plate injection molded with stomachs, which starts out at 15 millimeters. And there's some fibers that are retained at long lengths, but most of the fibers are in the shorter range, 1 millimeter or so. So if we take the fibers and we do a length, a number averaging in this distribution, we have about 1.29 millimeters in fiber length. The weighted average, which means the longer fibers count more than the shorter fibers, we have about double that length. So we have 2.13 millimeters. There is another way to represent, and that's the cumulative fiber length distribution, where that's that red line, and that's the integral of the distribution. And that one is maybe easier sometimes to see the difference of length distributions. Rather than comparing the length distribution, we compare the cumulative length distribution to make it easier to see the slight differences from one to the other one. And there's the N50 length. That means that 50% of the fibers, in this case, are longer than 0.81 millimeters. And that's, of course, where the cumulative residence time distribution is at 0.5. So that's a way to represent distributions. So if we look and see how can we assess, how can we do experimental work to assess what causes fiber attrition or fiber damage, let's look at, for example, the 20% glass fiber content. That's the graph on the left-hand side. We have 3 colored bars. The gray one is 50 RPM, then 100 RPM, and then 150 RPM of this Couette device that is on the left-hand side. So we built this Couette device where we have a very, very controlled flow. It's a shear flow, a simple shear flow that can be used then to assess the fiber damage and to be able to fit it to models. The Couette, we can control the temperature, so we can have different. Here we show different temperatures, 220, 250, 280 degrees. So we can see that the lowering the temperature 220, of course, has a higher viscosity than 280, which leads to less damage. So at 50, if you look at again the 50 RPMs, you can see fiber length of about going from 3 millimeters at 220 degrees to retaining about 5 millimeter length at 250 degrees. So the effect of temperature can be assessed, and the effect of RPM. But the other thing that you can see is as we move to the graphs to the right-hand side, the higher fiber content, you will have, of course, more fiber interaction, which we also see in the orientation models. And so the higher the fiber interaction, then of course the lower the length distribution. So all these things play a role, and so the question is what leads to, and there are models, of course, the one by Phelps and Tucker that uses a buckling model effect. So let's look at what causes fibers to break. So there are some experiments that my graduate student Avran Bechara did, where he did a loop of a fiber, 19 micrometer diameter fiber. And so by pulling the fiber, we can measure, and then you can see the breaking of the fiber at the end. So he recorded the point where the fiber broke. And there he recorded the radius of curvature, but he noticed that the radius of curvature varied from fiber to fiber. So there was a distribution of the radius of curvature, and the reason for that is some fibers are damaged; they have a little scratch on the side, and that leads to variability in the radius of curvature. So a perfect fiber, of course, that is nice and smooth can have a radius of curvature of 125 micrometers where it fails, but depending on the scratches, so you could go up to larger and larger radii of curvature in the system. So we included that in the results. So if you can see, for example, this is a fiber in shear, we can introduce that into it. So when we reach the radius of curvature, we break the fiber again. Here we don't see the buckling effect, but rather the ends of the fibers get broken off. And again, here is that the fiber continues on its Jeffrey orbit. It deforms. It turns very slowly, and then as it moves out of the horizontal position again, you can see failure. So this is of course simulated. But we simulated then several fibers. So this is work that Tina Chang did during her PhD thesis. And so she used a mechanistic model to predict the fiber attrition as the fibers were sheared. So we compared that to the Couette experiment. So you can kind of see over time how the system broke the fibers down. So basically, we start out with a higher fiber length, and eventually we reach an equilibrium fiber length or an unbreakable length. And so based on that, we build on a first order decay function where we have the L infinity. So you can see the upper equation, basically the length of the breakage is proportional to the length itself. Obviously, the longer the fiber, the higher the breaking rate, and eventually, when the length reaches the infinite or the unbreakable length, then you've reached an equilibrium where you no longer can break the fibers. So the shear stresses and stresses occurring during flow are no longer high enough to break the fiber. And so basically, you would have a function that predicts the length if you have a constant shear stress, where you would have a length distribution as below. The question is, what is Kf, which is the breaking rate, and what is L infinity? And so we did some conceptual thoughts here. So the infinite length is basically, if we just look at a flow, a Stokes flow past the fiber at a certain velocity, and the question is what is at which point do we reach the maximum stress at the edge in this beam, so where the beam is bent enough to be able to break, that would be the corresponding infinite length for those conditions that have a fiber viscosity and matrix viscosity and a fiber with a different fiber property. So you can see the equation for L infinity is the ultimate strength of the fiber, the diameter of the fiber, the viscosity of the matrix, and the rate of deformation that lead to some standard not including fiber interaction. Then, of course, the lambda as a function of phi is a parameter, a fitting parameter that takes into account the fiber content. You can see that parameter goes down as the fiber content goes down. So that's the average value of lambda for various experiments. And K sub f is a similar effect. So we have the breakage rate for different rates of deformation, and we can then attribute that obviously to the infinite length and to the length of the fibers of the original fibers, the initial fiber length. And so if we compare the model then with a simple shear flow using our Couette device and experimentally measuring the length distribution during the process, we can see how the model and the experiments actually match quite well. For the two different RPMs here, 150 RPM and 150 RPM. The other thing is we can actually, when we have the number average and the weight average, those are like the moments of the distribution, we can also then, in this case here, if we look at the experiments with the rheometer results, we can also recover the length distribution. So if we have the number average, the weight average, we can with that recover a distribution which is the measured distribution there in gray that you have. So the fiber length model or fiber attrition model was then implemented into Moldix 3D. And was tested with a simple plate. You can see the plate right here. So there are three locations 1, 2, and 3. For that, of course, we need the length distribution after the plasticating unit. So we start out, we do a purge of the injection molding machine, and in that purge, we measure the length distribution, and we use that as an input to Moldix 3D. So here, what we need to remember is we start out with fibers that are 15 millimeters long, and so we still don't have a model that works that can actually predict what occurs during the plasticating unit. And you'll see later that it's a more complicated issue. But if we have the purged length distribution, we can basically very well predict the fiber length distribution at the three locations, the number average and the length average throughout the plate. And you can see for different parameters in the model from Tina's work, we can actually fairly accurately predict that. That was then implemented together with our friends at SABIC and the people at Moldix 3D for this trunk lid, so demonstrated trunk lid that SABIC has. And it's a more complex. There's several gates there where you control when each gate is opened up during the process, but you can see in positions 1, 2, and 3, we can actually predict quite well the fiber length distribution. Again, here we have as an input the fiber length distribution of the purged material from the plasticating unit. But once we have that, we can actually predict quite well what happens during the process. And so that brings me to the final part. So there is an effect that hasn't been included, and that is the dispersion of the fibers. So if we look at the flow in the fiber breakage experiment during the Couette flow experiments, and do micro CTs at different times, so the input at times equals 0, you can see the fiber bundles completely together. After 5 seconds, there's still several bundles that haven't been dispersed. At 12 seconds, you can still see some undispersed fibers, and then again as you move along. So the fiber dispersion is really important. So for the experiments that we did, is we predisperse the fibers, so we can start out with dispersed fibers in our experiments, and so that needed to be done. But what about the process of dispersion? What happens in the process of dispersion? When we predispersed fibers using the Stomach's material, we did it at very, very slow rates that wouldn't cause any damage. Then once they were dispersed, that's when we did the experiments. So the melting and dispersion is something that occurs in the plasticating unit that has not been looked at in much detail. So the question is, how do fibers disperse? So we did a bunch of experiments using a sliding plate rheometer, where we have a simple shear flow and where the fibers get dispersed. And so we analyze the dispersion of the fibers, and we have a parameter S, which is the perimeter divided by the area. So these are so the coated compared to pultruded fibers, those are two types of long fiber reinforced thermoplastics. Coated are the ones that come where the fiber itself is just coated with polymer and extruded. The pultruded ones are the ones where the fibers no, the other way around. The coated ones are where we have a wax coating on the fiber, and then pultruded are the ones where the fibers already come a little bit more predispersed. And so we did a lot of micro CT analysis on the dispersion of the fibers using sliding plate rheometry, and to do the analysis using micro CT was found to be a great way to assess the dispersion of the fibers. So we can see the pultruded versus the coated ones, the standard deviation of the difference in the color of the pixels determines how we can how the fiber that is either coated or pultruded behaves differently than from one another, to be able to include that in our models. So the next thing my graduate student Hector Perez did was finding a coefficient of variance in the different X-ray or the micro CT X-ray devices. So, for example, if he shows the pultruded one on the upper left-hand side, at 0 seconds you can still see all the fiber bundles there. 5 seconds they're very well more dispersed. At 30 seconds even more dispersed, and then finally eventually you have one that is very well dispersed. So by looking at the color differences between them, so doing an image analysis and finding the coefficient of variance between the different images, we can then determine the dispersion factor, which is that epsilon on the lower right hand corner. So a reference sample, for example, you can see is 0% dispersion. So we match that reference sample as a 0% dispersion all the way to the completely dispersed value, and from that we can determine the dispersion of the fibers using the coefficient of variance. So using the actual images or the X-ray images, we can then assess dispersion in different samples. So here you can see, for example, individual values. So the dispersion, the pultrusion versus the coated on the right-hand side. is the using the same reference value. So, for example, the pultruded ones, they already have a certain dispersion within them. So they start out at, if you compare them 1 to 1 together, they already have a certain dispersion as compared to the coded values. So what we do is we normalize it and use individual reference values as for pultruded and coded as 0% dispersion. And so that's the left-hand picture by normalizing it to their initial dispersion value. So those are the measured values. Then what we did is we borrowed a model from Professor Manas Sloksovar, which was a dispersion of carbon black using the cohesive stresses and the stresses during dispersion. And we found that the model actually, the Manas Sloksovar model worked quite well in predicting the dispersion at different conditions, 210 degrees at 4 and 8 RPM, and then 250 degrees and 8 RPM. So varying the temperature, which varies the viscosity, of course, and varying the RPM. You can notice again here we're still using relatively low RPMs in our Couette device, but you can see the model compares well to the experimental data. The next thing that we did was to do pull-out studies and extruders to be able to understand what occurs in the plasticating unit and to see how dispersion advances throughout the system. You can see here at L over D, going from L over D 16 to 30. At L over D 16, you still have a relatively undispersed system, and then at L over D of 30, you are almost completely dispersed, which is what you want now. When you injection mold these parts, the last thing you want is to still have an undispersed bundle, and that's something that is of interest, and it does happen. And so we do want to understand the dispersion and the completion of the dispersion in the plasticating unit itself. So whatever is then comes out in the purge. So we used this would be the conditions that we used and the different changes, and we did in the pull-out experiments, we took out samples, we flattened out the samples, and then we did the micro CT analysis to get the images to be able to determine, using the images, we found coefficient of variance and the dispersion in the final along the L over D of the plasticating unit. This is not really truly a plasticating unit. It's the extruder. It's a 45 millimeter extruder that we have in our lab. But basically, the plasticating unit is an extruder with a reciprocating screw. So we can, by understanding what occurs in the extruder, we understand what occurs in the actual system. Let me see. So here we have the measured values at different parameters. So dispersion using different parameters along the extruder, along the different L over Ds. You can see we reach almost 100% dispersion at the end. The different RPMs, 30 RPM, 15 RPM. You can see how dispersion is affected by that. Glass fiber 30% and 40% with the coated pellets. So the fiber density, comparing pultruded pellets versus coated pellets in this dispersion. And we then joined that to a model, and this is just a very brief analysis. We used the melting model by Tadmore and Klein, and we applied the Manas Sloksovar dispersion model, and we were able then to compare then the model to to the experiments. And one of the things that we found is that dispersion doesn't start until about a melting of about 25%. So where the solid bed is about 25% of the width of the channel, and that's where basically we know that dispersion begins. So we can see that there for the different parameters. And then we used the melting model and the parameters in the extruder to compare the dispersion, and we can see at least we can compare dispersion quite well in the plasticating unit or in the extruder itself for different parameters. You can see several data here, so it works quite well. This is being currently written up for a paper in polymer composites. So you can see the comparison of the experimental data and the 1D Newtonian flow, and then also the COMSOL data using non-Newtonian data, and you can see the prediction of the dispersion works quite well. We compared models at higher RPM, including the morphological parameter to the model. We did the measurements, measured fiber length through the screw length, and we included the Manas-Sloksovar model. And one of the things, this is where I want to end future work, though, is what we did is here you see the dispersion in the solid lines and the fiber length in the dashed lines throughout the plasticating unit. And so this would probably be a beginning of where we know that the dispersion actually is completely coupled to the fiber damage model, because undispersed fibers, when they're still close together, they protect each other. So low dispersion means low fiber damage, high dispersion means higher fiber damage. And so we have a coupled system that needs to be solved. And so that's what my graduate student, Paula Hohoff, is doing right now, is she's trying to solve the coupled dispersion and fiber attrition model for predicting fiber attrition in the actual plasticating unit of the injection molding machine. And so that brings me, sorry I sped up at the end. I saw I was running out of time here. So, but you can see where research is going and where it has come. And of course, this is work that has been going on for the past 40 years by many research groups and people involved, in particular, Chuck Tucker and his group at Illinois, my former advisor. Thank you.
Professor Osswald, thank you very much. And I'm Jonathan Goodsall. I'll be handling a couple of questions here. We have time for a couple. And just again, thank you. And let me ask, one question's come up a couple of times in here about, you're probably not surprised, nanotubes, basically around the size of the fibers and how much this does or could apply to things like nanotubes. People have indicated a little bit of carbon black, but can you comment on the applicability of this if you change the size of the fiber down to a nanoscale, or if we change the shape perhaps to things more circular or spherical?
Yeah, so I think obviously if you have nanotubes, there's all kinds of other interactions that occur between the fibers. And of course, how do you, with attrition, obviously, how do you measure that, right? And so I think models are only as good as you can measure whatever happens to them. So I'm sure orientation and stuff would apply to this, but you would likely have to include, and to tell the truth, I've never did work with nanotubes in any of this work, but I'm sure there are other interactions that play a role with nanotubes for orientation, for other things. And in attrition, I'm not sure how one would deal with that and how would even measure that. Now, for platelets and stuff, I mean, obviously this work has to do with fibers, with elongated fibers. But of course, you could also do this with platelets. We did work years ago in painting processes for Mercedes-Benz, where the metallized colors are really these little platelets, and the orientation of the final platelets on the surface of the painted body plays a role in how color and how light is reflected from that surface. And obviously, you need to modify then the models. The existing models, of course, are for elongated, longer fibers, but you can basically also change the models by introducing the effect of velocity gradients and to the deformation of platelets. So it would also the models would be slightly different, but there's still the interaction effect, etc.
Thank you. That hopefully gets those folks who are hankering down that path a little bit of a guidance where they can go. Let me ask one more question. I know we're coming up on the hour, but one more question popped up about the edge weakness you pointed out. Someone asked, are there ways we can improve that? I'd like to give you a chance to comment on that.
On which weakness? Sorry.
The edge weakness near the edges where you have fewer fibers.
Yes, and that's a huge problem. So in fact, I even have a Mercedes trunk lid sitting here in my office, and the edge is completely crumbled. And that would have to, when people would have to play with formulation, with viscosity of the resin. But yeah, unfortunately, in compression molding, fibers that are the way the compression molding process works is as you move closer and closer to the flow front, materials move faster and faster, which means the fibers that stay behind are kind of dragging the fibers in front of them and not allowing them to move as fast, which inevitably will lead to some fiber-free region right at the edge. Now you can deal with that by increasing the viscosity of the resin. That would, of course, increase the drag forces imposed on the fibers and would reduce that region. And so I think having a region that is free of fibers at the edge is almost inevitable. But one can minimize its size.
Thank you for that.
But there's a lot of work. There's work to be done in that area. Oh, and I just saw Chuck Tucker is in the audience saying hello. Hello, Chuck. Hi. Sorry.
This is
my PhD advisor and good friend Chuck Tucker, and probably the most influential person in the fiber orientation area and fiber microstructure. So I'm honored that he's here today.
Well, we're glad you've been here. We're glad, Mr. Tucker. We're thankful for all the audience. And again, to everyone, this is being recorded as our previous talks. You can find those on cdmhub.org. This is the last webinar here for the spring. We will resume again in the fall. So be looking out for reminders from us. But for now, we wish you all a good day and thank you all. And again, thank you to Professor Osswald. We'll look forward to seeing everybody again in a few months.
Yeah, thank you very much. Thanks for the invitation. It was a pleasure. Yeah.